Well, hello, Math 251 students. Good to see all of you. Welcome to my seminar room at Cal State Fullerton. I'm going to jump in here with a video to kind of give you some examples and a little bit of the last part of Chapter 15 that I haven't covered yet. I hate to wait till Tuesday to teach it to you, so I hope you'll enjoy the video. I'm also going to be inserting some little extra credit into the video. Every time I write something on the board for extra credit, if you get it right and put it on your homework assignment for Tuesday, you'll get a half of a point of extra credit towards your final exam. So that's pretty significant. So there's going to be several of those, so pay attention. And hopefully this will help you learn the material as well. So we were talking the last time in class about calculating flux integrals. And that's really the topic of section 15.6. Turns out that in certain situations there are some nice shortcuts for calculating flux integrals. One of them is if you have a surface S that is closed. So here's a picture of a surface that's closed. If it's closed, then there of course is a solid body inside that surface, which we usually call Q, a three-dimensional solid object. And what we can do, as it turns out, is calculate the flux integral. That's what I've written down here on the left side. We can calculate that flux integral by converting it into a triple integral. The nice thing about the triple integral is that there's no vectors in it. The divergence of the vector field, if you remember, if you have a vector field, I'll just remind you here, if you have a vector field MNP, right, then the divergence of that is no longer a vector, right? You simply add up the scalar partial derivatives of the three components M, N, and P with respect to x, y, and z respectively, and that's what you're going to be triple integrating here. Since it's not a vector expression, this is just a triple integral that we can do using the chapter 14 material that we have learned. Okay? So this is called the divergence theorem. The divergence theorem is one of the most important theorems in vector calculus. All right? I'm not going to take the time to prove the theorem right now. Basically, the idea is that the flux that is emanating out of a closed surface, remember that our ds vectors, our perpendicular vectors to the surface, are always oriented outward if we are going to use a closed surface. So the positive direction is outward. So we are measuring the flux out through this surface, which is really measuring the tendency of the vector field to spread apart. Yeah? That's what the divergence is doing. It's calculating the tendency of the vector field to sort of spread itself apart. So conceptually, there is definitely a relationship between the flux through a closed surface and the triple integral throughout the solid of the divergence of that vector field. Okay, so let's just do an example here. So by way of an example, the first example I want to try is let's compute the surface integral of f dot ds where, okay, so the vector field f is going to have components x cubed, 2xz squared, and 3y squared z. Okay? And s, I have to tell you what the surface is as well, s is bounded by the xy plane and the surface z equals 4 minus x squared minus y squared. Okay? One thing you definitely need to be thinking about over the next several days is what each of the surfaces that we've learned back in chapter 11, what they look like and what their equations are. This is a paraboloid, so you need to make sure you know that, right? That's going to be very important. Let me try and draw a picture of the situation we have here. My xy plane is down at the bottom. This is an upside down paraboloid, right? It goes through the z-axis at 4, and then it hits the xy plane, which is when z is equal to 0, at the circle x squared plus y squared equals 4, right? If we set this equal to 0, x squared plus y squared would equal 4. So you can see our solid object Q is right there, okay? So calculating the flux directly, if we wanted to calculate the flux directly through this closed surface, this is the whole thing is S, right? We would actually have to do two different flux calculations, right? We would have to calculate the flux through the paraboloid, and we would have to calculate the flux through the disk at the bottom as well, right? So that would be a fair bit of work. So luckily, we have our divergence theorem, which I'm going to erase right now. But nice thing about the video, you can always go back, rewind it, watch again anything, put it on pause to think about things. Feel free to do any of that. Okay, but let's try to calculate this flux integral by using that divergence theorem, okay? So I'm going to calculate for the solution, I'm going to just calculate the divergence of F. So how do you know that you should use the divergence theorem? The real key to that is the fact that your surface is closed, right? You have a closed surface here. That's the trick, okay? So the divergence of this vector field is going to be the partial derivative of x cubed with respect to x, which is 3x squared, and then the partial derivative of 2xz squared with respect to y, which is 0, and then the partial derivative of 3y squared z with respect to z, and that's just 3y squared. So there's the divergence, okay? So my flux integral here, double integral of f dot ds, is going to be the triple integral over q of 3x squared plus 3y squared dv. One of the reasons that chapter 15 is so important in terms of helping us to have the big picture of the whole semester is that we often find ourselves solving problems from earlier in the semester here, right? So this triple integral would be an example. We want to do the triple integral over q, right? Well, what I hope that you're thinking about here is the fact that the base of the solid is actually a circle, it's a disk. So in situations like that, we are often well advised to convert our triple integral into cylindrical coordinates, basically polar coordinates, right? Because I've got a very nice disk on the bottom. So I could actually implement that change of variables right now. Theta would go from 0 to 2 pi, and r would go from 0 to 2, right? So that's just on the disk on the bottom. And then z goes from the xy plane, which is z equals 0, up to the paraboloid itself, which is 4 minus x squared minus y squared, which can be thought of as just 4 minus r squared, okay? Then we have our integrand here. 3x squared plus 3y squared is actually just 3r squared. And then don't forget that we have a Jacobian, which is r, dz, dr, d theta, right? Okay? So this would be the triple integral that we have to calculate. We can pull down the 2 pi right away for the theta integration because that doesn't occur anywhere on the inside of the integral. We also have a 3 that we can take out, so I'll go ahead and do that. We're left with the integral from 0 to 2 for r. The integrand here, we have r cubed, and then when we do the dz integration, from the top to the bottom, we just subtract, we have 4 minus r squared right there, okay? So this is 6 pi. Let me just multiply out the integrand that I have here. I have 4r cubed minus r to the 5th dr, okay? And so if I take out the 6 pi again and just do this integration, I'm going to get r to the 4th minus 1/6 of r to the 6th. Okay? Evaluate that from 0 to 2, and we get 6 pi, hope you guys can read this okay, it's down on the bottom of the board here, 6 pi times, when I put in 2, I'm going to get 16 minus 64 over 6. So this whole thing, if we work it out, yeah, that is the right expression. If you simplify that, it comes out to exactly 32 pi. Okay, it comes out to exactly 32 pi. Okay, hopefully that makes sense. So that's an application of the divergence theorem, 32 pi. I am going to do a quick little follow-up question while I've got you here thinking about this example. So I'm erasing this calculation, but you can always pause and go back if you need to, look at it again. I want to imagine for a second that the paraboloid portion of this solid, or of the surface I should say, is S1. And I want to imagine that we were asked instead to compute the flux integral of F through S1. Just that much. Now, if we're only looking at S1, then the surface is no longer closed, right? There's a top side to the surface, and there's a bottom side to the surface. So I am going to have to declare, in the case of a surface that's not closed, I have to declare which side is the positive orientation. So let's just assume that this is with upward positive orientation. Okay? Now, the thing is, we could do that calculation if we wanted to. We would be doing it directly using this vector field. Now, here's the issue with it. The issue with doing that is this is going to be messy. We can parameterize the paraboloid, all right, okay, and calculate r sub u cross r sub v, dot it with, the vector field here. But the vector field here is, maybe not so nice. So here's what I'm going to suggest that we do to calculate this. I'm going to suggest that we go ahead and we imagine that we decide that we're going to add a second surface, which the second surface is going to be the disk on the bottom here with downward orientation. Okay? So with downward orientation. So this is ds2. And these vectors here are the ds1 vectors with the upward orientation. So I'm going to view the flux integral through the disk as having a downward orientation. You're going to see why in just a second. But of course, if I do that, I have to subtract it right back out again. I can't just put something in and then leave it there. So as you can see, guys, I haven't done anything. I added something and then I subtracted it right back out again. The thing is that this first part right here, if we add the flux through S1 to the flux through S2 with the orientations that I have already given you, then that is a closed surface, right? This whole thing is just, the surface integral of the original S, the problem that we already had solved earlier, right? So we already know that that's going to be 32 pi because we did that a while ago. Okay, and then of course I have to subtract this flux integral over here. Guys, what I'm doing right here is I'm trading this rather difficult flux integral through this rather difficult surface for what I think will be a much easier flux integral. So I'm going to do this one directly. Okay, I'm going to do the flux through the disk that's on the bottom of this paraboloid with a downward orientation. I'm going to do that one directly. Okay, so let's, well, I need to keep the vector field on the board here. So let's parameterize S2. Okay, so, it's a disk, right? So hopefully we remember that a great way to parameterize a disk is with the polar coordinates. And in this case, the z is 0 because we're looking at the xy plane, right? So there's your disk. And I can calculate now the r sub r cross r sub theta, because those are my parameters. I, j, and k are here. Okay? So I differentiate with respect to r, and I'm going to get cosine of theta, sine of theta, and 0. All right? And when I differentiate with respect to theta, I'm going to get negative r sine theta. I'm going to get r cosine of theta, and I'm going to get 0. Okay? If we calculate that out, the I component is going to be 0, the j component is going to be 0, and the k component is going to be r. Okay? By the way, theta goes from 0 to 2 pi, and r, this is a disk of radius 2, so r goes from 0 to 2. This is the wrong orientation because notice that the k component is pointing upward, but we had already made the decision that we want the orientation to be downward. The reason that we want the orientation of the disk to be downward is that we need this to be, in order to use the divergence theorem on the first two integrations here, the surface has to be oriented with positive outward normal vectors. Well, outward, for that disk on the bottom, the outward direction is actually the downward direction, right? So I need to fix that with a minus sign. So I am going to use my ds vector is going to be 0, 0, negative r dA. So the minus sign just turns the vector around and gives it the proper orientation. Okay? Now here's the amazing thing. When you do, and this is ds2, right? The downward normal. When you do f dot ds2, here's f, right? But remember that z was 0, right? Well, here's a couple of places where we have a z. So in the vector field f, if we're in the xy plane, there's only an I component, right? We only have an I component here, which means that those vectors are perpendicular to the ds2 vectors. When you dot these guys together, you just get 0. Guys, this second integral here is just 0. The dot product is just 0. We don't even actually have to do the integration because the function that we're integrating was just 0. So, the final answer is 32 pi. Okay, I have a little extra credit for you right now. On your homework assignment for Tuesday, I want you to write down the name of my cat. My cat is a sweetheart, so I like everybody to know about my cat. My cat's name, so next to number 1 on your homework assignment, you're going to write my cat's name, which is Ginger. Okay, I'll try to bring a picture so you can see my beautiful cat. Ginger is my cat, and that's the first bit of extra credit for the homework assignment that you're working on for Tuesday, which is actually extra credit for the final exam. Okay, Ginger. Make sure you get that down. Okay, let me give you one more example of this divergence theorem, and then we'll move on to something else. Okay, let's suppose we have the following. I think I'm going to do one from the book here that is a nice alternative to the one we just did. Okay, so let's calculate the flux integral of f dot. I just want to remind you the book will write the flux integral that way with an n vector. But this is really just in my notation, which I like better. And I am going to use my notation on the exam, for instance. So just be aware of that. We're going to calculate this thing. So we're going to compute this flux where the vector field f, let me give you the vector field here. It's going to be xy, comma, yz, comma, negative yz, okay? And S is bounded by z equals 0 and z equals the square root of 9 minus x squared minus y squared, okay? So there's a problem that we can solve, okay? All right. So let's draw a picture of the surface here. So there's I've basically given you what the boundary of the surface is. The little picture is a good idea. Hopefully you are aware that what we have here is the equation of a hemisphere. It's the top half of a sphere. The sphere has radius 3. Okay, so I'm just going to draw it right there. This is a sphere of radius 3. Okay, so we have z equals 0, which is the plane where the disk is, right? So again, we have it's actually not that different from the last example. We have a closed surface here. Okay, if they didn't give us z equals 0 and they just said find the flux through the hemisphere, right, then we would not be looking at a closed surface and we would not be able to use the divergence theorem directly. We might be able to include the surface on the bottom of the hemisphere, so then that would be two surfaces. Put together, they of course form the closed surface, but then we would have to subtract out the flux integral through the disk on the bottom. Right. Okay. Right, see on the last example, I had asked you to find the flux through the surface S1, but it turned out that the flux through the surface S2 was a lot easier to calculate because the F dot ds turned out to just be 0. The idea there was that the flux through the disk was simpler to calculate than the flux through the paraboloid. And by using the divergence theorem to sort of make up the difference between those two fluxes, we were able to basically solve the problem of the flux through just the top paraboloid surface relatively easily. Okay. So, okay, let's go ahead and try and do this one though. This is just a hemisphere. So I'm going to use the divergence theorem. So this is going to equal the triple integral over Q of the divergence of F dV. Okay. This is going to equal, let's calculate the divergence right now so we know what that is at least. So the partial derivative with respect to x here is y. Partial derivative with respect to y is z. And the partial derivative with respect to z is negative y. So we end up getting just the triple integral over Q of z dV. Okay? Now, this is integrating over a hemisphere. So the natural choice of coordinates to use for this is going to be spherical coordinates. So let's try to set it up in spherical coordinates here. Theta, of course, would go from 0 to 2 pi. Phi would go from 0 to pi. We're doing the whole entire sphere, right? The sphere has a radius of 3, so rho will go from 0 to 3. Z, if you remember, is rho cosine of phi. Okay? And then the Jacobian for converting to spherical coordinates right here is rho squared sine of phi. And then we have d rho, d phi, d theta. Okay? Well, the theta integration, again, can be done immediately. We're just going to get 2 pi out of that. When we integrate the rho, notice that I have 3 of the rho's there, rho cubed. So when you integrate rho cubed, you're just going to get 1/4 of rho to the 4th, which is going to be plugged in with 3, so 3 to the 4th. And then you're just left with integrating cosine of phi, sine of phi. Well, if you just let the sine of phi be equal to the u, then the derivative of that is the cosine of phi. You're just literally integrating u du. So you're going to get 1/2 of, well, it'll be the sine squared of phi. And that's from 0 to pi. And the answer to that is 0, right? Okay, when you evaluate the... Oh, you know what? I'm making a mistake, aren't I? I'm making a mistake. We're only looking at the hemisphere. I barely caught myself. That should be a pi over 2. And so this should be a pi over 2 as well. I wondered about that because I didn't think the answer was 0. All right, so we put a pi over 2 there because we're only, remember, phi is measured down from the top, and we're only going down to the xy plane. All right, so the 2 and the 1/2 cancel, and we just get 81 pi. 3 to the 4th is 81. 81 pi over 4. Sine of pi over 2 is just 1. So, all right, so there you go. Guys, one of my favorite hobbies is climbing mountains, as you know. I have a house out in Colorado, and I'm going to be going out there in a couple weeks, so my mind has been on this a lot. And I've climbed all 58 of Colorado's 14,000-foot mountains, and I can see one of them from my house. So for your second extra credit item, I want you to write down the name of the mountain, the 14,000-foot mountain in Colorado that I can see from my house. I'll try to bring a picture of that to show you as well. It is called Long's Peak. Long's Peak. So this is your second extra credit opportunity right here. Long's Peak. It's the mountain that I can see outside of my house in Colorado. Okay. let me move on. There is one more theorem that I want to cover, and it's really what is in section 15.8. It's called Stokes Theorem, and I'm going to write it down for you. So again, before I move on, the divergence theorem primarily is used to handle fluxes that are calculated through a closed surface. Okay, it's through a closed surface. So Stokes theorem is not like that at all. So Stokes theorem 15.8 here. Stokes theorem does not involve a closed surface at all. What it is a surface that you want to find the flux of something through, but there of course is a boundary curve to that surface that you're going to be looking at. So I'll just draw a picture here. Maybe this is a curve C. Okay, so we're kind of back thinking about line integrals. That could be the boundary of some crazy surface here, right? This is just a surface that's sitting up here above the curve. So think of it like it's a balloon, you know, that's like whipping around in the wind, and this is maybe, or maybe it's, you know, your tent or whatever, and they've got this curve that's on the ground that's sort of staked down. It doesn't move. This curve doesn't move, but then the wind is like blowing this surface in some kind of a crazy shape. If you've ever tried to like shake a trash bag open or whatever, right, the boundary of the trash bag is like the curve C here, like that's the top of the trash bag, and then the wind is like blowing the whole rest of the bag in some crazy configuration like this. Okay, so this is kind of the setup for this. So let me state what Stokes theorem says right here. Okay, so Stokes theorem is the following. Okay, it says the following thing. Okay, let S be a smooth surface bounded by a simple closed curve C. So the surface S is up here, right? Simple closed curve C with compatible orientation. I'm going to talk about the orientation in just a second. Just want to get the text of this up here first. Okay. Then it turns out, so you can actually use Stokes theorem to calculate the line integral of f dot dr. Okay. And it is a surface integral over S of the curl of f. Okay, so remember the divergence theorem, we used the divergence, of course. Here we're going to be using the curl of f dotted with ds. Okay? So the curl measures the tendency of the vector field to rotate. Okay? And the line integral is sort of the work that's being done as you traverse the curve. If the vector field is conservative, well, then this is a closed curve. Line integrals of conservative vector fields around closed curves are 0. And we also know that the curl of a conservative vector field is 0. So in the case of a conservative vector field, this equation is just 0 on the left and 0 on the right. We don't really use Stokes theorem in the case when f is conservative. There's no need to, right? We already know that line integrals around closed curves are going to be 0. But if we have a vector field that's not conservative, well, that's the situation where it can be useful to use this theorem. You know, in the case where you're just in the xy plane and you just have some curve here like this, and you have a domain that is on the inside of the curve, this Stokes theorem, if you remember, we actually had a theorem already that talked about calculating the line integral of a closed curve around you know, a vector field just in the xy plane, and it was Green's theorem. And if you remember what